Welcome to our demonstration video. In this video I'm going to go through the thermal analysis process, beginning with modeling and then moving to pre-processing and solving, and then post-processing and looking at our results in our graphical post-processor. So to begin the analysis, we're going to come down on the taskbar here and click on the Analytical Methods Manager. It brings up the program, and we have our session manager here. So we're going to begin with modeling, so we'll go ahead and continue there. And for the demonstration here, we're going to be running a macro in our modeler. So let's go ahead and click New and then FlexGen to bring up the modeler. So the model we're going to be building is a thick-walled copper tube that is very long, and it is originally at 0 degrees C, and it is touching a wall at 100 degrees C. And we will compute the transient temperature distribution in the tube over a period of 50 seconds. So to build the model, we're going to be running a macro here in FlexGen. So the macro is a series of commands that have been previously executed and saved that build the model. So I'm going to do that. We'll come down here and we hit File, Macro, Run, and then I'm going to do it in the pause mode so that we can discuss what's going on. So it pulls up the list of macros we have here. We're going to run the thick-walled tube. So we'll double click on that. So the first thing we're going to do is insert a node at a radius of 1 centimeter, and then we're going to copy that node 5 times with an increment of 0.4 centimeters, and it creates 5 nodes. So we'll set our node labels on so that we can better see the nodes, and we'll paint those. So those are our first 6 nodes. So we're going to zoom in a little bit here a couple of times. Now we're going to copy those 6 nodes, and we're going to do that 17 times, and we're going to rotate them around the z-axis here to form the cylinder. So 17 times we'll do a angular increment of 20 degrees, and we create our 102 nodes here, and we'll zoom all and get them up on the screen. So now we need to insert an element or insert the elements. We're going to use plate 3s, which are triangles, and we have to create some properties. Element property 1 here, we'll create that. Now we're going to go with this standard material, and it'll be our standard material number 85, which is copper tube, or just copper. The thickness into the page here is going to be 0.01 inches. It could be anything really. This is an infinitely long tube. And we'll take the defaults on the rest. We'll call this just a thick wall tube section. And the group, where the elements will all be in a group, and we'll call that thick wall tube group. And now we start creating the elements, and we put our first one right there, our second one right there, and then we'll copy those elements 1 and 2, and we'll do that 4 times and go out radially, node increments of 1, and there we have created our 8 elements there. Now we're going to want to copy those 10 elements and do an increment of 16 around the cylinder. Plate 3s, node increment this time is going to be 6, and we create our 160 elements there. Now we just need to finish up that last row of elements there, and we'll kind of pound in the node numbers for those, copy those 2, and go out 4 times, and there we have all of the elements that we want now. And so we've got 180 elements and 108 nodes here. Now I'm going to insert a load, and we're going to put it over here on node 6 here. That'll be the cylinder touching the wall here. And that's going to be an element thermal load. And the temperature of that is going to be just a fixed temperature of 100 degrees C. And it'll be on node 6. So you can see the load symbol there, the little red square showed up. That's the load. We'll turn off our node labels there, and we'll set the title of the window here as thick wall transient, thick wall tube transient. Change the size of that up to 0.3 inches. And there is our completed model. So we have all of the elements, copper material, we have a load here, and now we want to save the thermal model. And we come down here and we say File, Save, Finite Element Thermal Model right there. And we'll do thick walled tube. It's already there, so I won't bother overwriting that again. And we're going to want to now, we can exit this, and we've already saved this model here in another session, so we'll just get out of this. So now we come back to our modeling dialog here. We're done modeling. We want to hit back here, and we want to go to thermal analysis. And we'll hit continue there. So now we want to select the model name that we're going to run the analysis on, and that's thick tube FTM. By the way, I had to insert a analysis property back in the modeler there that gave us the time step, the stop time of 50 seconds. The time step was actually 10 milliseconds, and then there's a print interval also. So how often do you want to see the results? And I selected 2 seconds for that. So now here we go ahead and select the FTM model there. We could actually double click on this and just it'll get pulled up here in WordPad, and you can look and see what the model actually looks like, just a text file of what the model looks like. There's the stop time, the print interval, and the time step. So we'll close that up. And now we come down here. Once we highlighted that, that enabled a number of the segment executables down here. We know that it's a transient one. It read that file and said, okay, it's a transient analysis, and enabled those segments there that we can run. So we could run all of these individually, the preprocessor, the solver, the postprocessors, or we can come over here, we can just hit transient, and you can see which ones of those it's going to automatically run. So we'll do that. We'll hit transient. Flux 1 is the preprocessor, computes all the conductance matrices for the elements, writes out everything that the solver needs to see. Fluxpro is a profile minimizer, reduces the bandwidth of the conductance matrix. And we got a 10% improvement there. And then Flux 2T is the transient solver. There's only 108 nodes, 108 equations. There are temperatures at each node. So that's done. It solved that. And now Flux 3 is the post-processor, and it's going to be writing out data for each one of the time steps. So we've got 180 elements, and then we have 25, 26 time steps. So the 12 here will go up to 50 seconds is the final time. We'll just wait for that to conclude, and then we will go look at the results then in our graphical post-processor. Now at the end of this, you could go pull up some text files and just look and see what the results are for each one of the elements, and then you can pull up the text file from the solver and see what the results were from a temperature standpoint at each one of the nodes. So this is about to conclude here, and then the post-processor will come up automatically here. One more time step. Okay, so that's completed. Okay, so now we're in the graphical postprocessor. It automatically pulled up the model here, and it's skewed in space here because of the view direction. So we'll just come up here over to the command bar and hit one of the view directions there, and it will straighten it out. So I want to make sure that we've got it oriented correctly. So we did tag node 6 with the load, so that is indeed node 6 there. And then all the way across the model here, it's node 60 on the other side. So we'll be wanting to graph the temperature distribution over time for node 60 here. So, okay, so now we can take a look at the data. We can hit data here and pick a time step. So what time step would we like to see the results in? So I just picked time step 15, and it's that time 28, and we'll hit OK. And there's the temperature distribution throughout the model at that time step. Now we can just go back and so something to note here is that the temperature scale here is the min and max of that particular time step. We can also go hit the flip button here, and it will march through all of the time steps, and it goes from the scale is over the entire transient time. So it started out at 0 degrees C and it wound up at 100. So now you see at the final time step, everything is red here. So we know that the temperatures are between 81 and 100 because they're all red. So I can go ahead and hit data here again and put in 26, which is the final time step, hit OK. And now we see the temperature distribution in that time step, and it goes from 83 degrees to 100 degrees. Okay, now if I want to go ahead and to graph some of the results over time, I can hit the graph button here and pick a node. So I can pick a number of nodes or a range of nodes. I'm going to pick node 60 because that was the one on the opposite side there, and we'll color that scale red and hit enter, and then we're going to go ahead and do 30, and we'll make that a green one and hit enter. Now we'll just hit OK. So there are the two nodes that we just looked at, and you can see that over time there they all both start out at 0, rise up to this one was 83 degrees, I believe, or 81 C. So we have the capability to do that. We could change the axes, the time duration, whatever we want to do there. We can pick different nodes to look at. So we'll go back to data and get a time step that's in range. And this is at 48 seconds. We can step through these just by hitting the time minus button. It'll walk down through there. And you can notice that the scale is changing here also. So you can do a lot with the model, especially a three-dimensional model. This is a fairly simple model for demonstration purposes. We can also turn off the boundary here on the elements, turn that back on, and we can contour it rather than going solid. So sometimes it's good to be able to see the gradients in the data here as we go through it. So we can also see there is some other data here to be seen also. And we could go to comp, and we'll go comp minus. There's some energy information that we can look at. Conduction. Let's go to stored right there, and we could flip through that. You could see the energy storage stored in the various elements there over time. Okay, we can zoom in. We could, let's just go to take off the contour mode there. That's it. We can go to zoom, come in on a particular area here, hit that. I want to go comp up. We'll go back up to temperature. Do that. We can put the data there on nodal temperatures are. Zoom all. You can see all the nodal temperatures there. We can do also put that element data in there also, zoom in. So you can do a lot with it, toggle various options on and off, get a bitmap of it, change the background to white depending upon what type of bitmap you want to look at. So, all right, so that's going to conclude the transient thermal analysis demonstration. So I'll go ahead and click stop or exit. Yes, I do want to exit. And out we go, and now we exit out of Flux, and we're done. So thank you very much.